Yes, Dr. Ali, you may start your lecture. And thank you so very much for
You're most welcome, ma'am. And thank you for giving me this opportunity. Hello, everyone. I welcome you to this session on early development in modern AI. Specifically, in today's session, we will talk about foundations of graph-based search. We will see a popular heuristic search, and finally, we will end the session with a popular adversarial search algorithm. So let us start with the graph-based search. So at first, we need to know what is the search problem. In our day-to-day lives, we face several problems. Like here we can see a 15 puzzle game where the player need to arrange these numbers in a ascending order from an random state. This is also a such problem. Also, we have seen these problems with it is popularly known as maze problem, where we start from a position and we need to find our way through this complex maze, and we need to go we need to reach to the end of this maze. This is also an example of a such problem. And we regularly use Google Maps, where we search path from point 1 to point B, and we see that Google Maps finds the route considering various criteria. This is also another example of such problem. So now we will look into the such problems in a more formal way. For this, we are getting to introduce with some terminologies. At first, we will see what is agent. In AI, an agent is an entity that perceives its environment and acts upon that environment. We also need to use a concept called state, which represents a configuration of the agent and its environment. We will see examples very soon. Here, with respect to our 15 puzzle game, all three boards are three states, because each has different settings of numbers. We usually start with an initial state, which is our input. For example, if we are given this board as the initial as our initial state, we need to make ways to rearrange this board into the final state. At each state, the agent or the AI program need to make choices, and it has several choices among which it needs to select the most intelligent actions. Now we are representing these concepts using mathematics, because we need to use computer to solve these problems. So we are translating these languages into a formal approach which the machine can easily understand. So to represent the actions, we have a function named actions, which take input s, which is any state, and it returns all possible tasks or moves the agent can make from this state s. In this example, let us consider the 15 puzzle board. At any state, we can shift those tiles into to the right, to the left, to the up, or to the down. So these are the actions, but not all actions are legal based on a particular state. So based on our actions, we will get new states. We represent this concept using a transition model, which describes what states results from performing any applicable actions from the input state. So we represent this concept using another function, which takes an input as s, which is the current state, and an action which is a legal move available at that state, and it returns the new state which is available after executing action A on state S. So in this example, we are given a state of 15 puzzle game. Here is the blank cell which can be moved left or up position. There are two valid actions available. So if we select actions, then the resultant state will look like in this way. And if we consider another action, then the resultant state will be different. So this is how we represent the transition model in a mathematical way. So based on this transition model, we will get a lots of states and way to move around between those states. We will collectively call this thing a state space. For example, in case of 15 puzzle game, this is a small fraction of the overall state space, where we see that these board are represent different states, and these arrows represents a valid move that convert one state into another. So this is a specific example for 15 puzzle games. So we can represent this concept in a more abstract way, which is a graph where these circles are known as states, and these edges are this agent represents an action that is available at this state. So that's why these approaches are known as graph-based search, because we formulate our input problems into a graph. Another concept is required to solve this problem, which is the goal test, which takes a particular state and it returns that whether this is our expected final state. And the next concept is known as path cost. If we consider the Google Map example, which gives us a path from point A to point B, we are not interested in any path, but we are interested in the shortest path. In this way, each problem has an associated cost. So we also need to consider these cost elements into our problems. So one way to represent this concept of cost into the state space is the weight of these edges. For example, we see that from state D, the action cost us 6, and from state H, there are several of actions available. Some cost low and some cost high. In some problems, we have the same cost for each actions. Like we already take the example of 15 puzzle games, where each action is basically represents moving the tiles, where there is no more or less concept in this cost. So using all concepts, we can formally define a such problem. The solution of this such problem is a sequence of actions that lead us from the initial state to the goal state. And as we already know that we usually interested on the optimal solution, which is not only gives us a path from starting state to the goal state, but also it makes sure that the cost of the path is lowest or highest depending on the definition of the problem. Now, to solve this problem, we need a data structure which we call the node, which collectively represents several related informations. So to solve such problem, the node need to have 4 pieces of information. It represents a state of the problem. it also need to tell us the parent, which is the node that generated this node, and it also need to be stored the action that resulted this state from its parent state, and it also stored the path cost, which represents the cost that incurred from moving from the initial state to a particular state. Using all these informations, we will try to develop some algorithms for solving our such problem. So what we will do is we start with a data structure which we call frontier, which stores the states, the nodes that we need to explore. Initially, this frontier is empty. Initially, this frontier contains the initial state, and as the algorithm moves, this the structure grows, and sometimes it shrinks, and finally, if we successfully solve the problem, then one of the node that this frontier contains must be a goal state. So we will do we will repeatedly do some steps. At first, we will check whether the frontier is empty. If the frontier is empty, then there is no solution. This is important to know, because not all such problems are solvable. So if we start to solve a problem, and at some point we see that the frontier is empty, we know that this problem is not solvable. At the next step, we remove a node from the frontier, and we will see very soon that the order of removing the node is very important to improve the performance of any search algorithm. After removing the node, we check that whether the node contains the goal state. So if we find that the node contains the goal state, then our search is completed, and we can form the solution of this problem. Otherwise, we need to expand this node. By expanding node, we means that we need to find the nodes, the neighboring nodes, which can be reached by executing valid actions, and we need to add those new nodes into the frontier. So let us take an example. Here is a hypothetical graph which represents a search problem. So we are trying to find a path from node A to node E. So we will start with our initial state in the frontier. Then start the loop. We remove the initial state from the frontier, and we check that whether it is a goal state. We see that this is not the goal state, so we expand this node A, which means we are adding the neighbors of node A to the frontier. So now we considering node B, and in the same way, we see that this is not the goal state, so we add its neighboring node, which is C and D, to the frontier. Now we have two nodes in our frontier. So in this example, we arbitrarily took node C, and in the same way, we see that this is not the goal set, so we add its neighboring nodes to the frontier. And now we have two nodes in the frontier. We arbitrarily take node E from the frontier, and now we check we find that our goal set is inside this node E. So the search process is end here, and our we can form our solution, which is the path from A to E in this example. Now we need to think what might go wrong in this example. this is another example very similar to the previous one, but with one difference. Here we have a reverse edge from node B to node A. So in this example, we start in a similar way with this initial node. Then after considering node A, we add its neighbor B to the frontier. Then we consider node B. Now in this step, node B has 3 neighbors. So all of those neighbors will be added to the frontier. If we are unlucky, we choose to consider node A, then in the worst possible scenario, we might stuck into a infinite loop where we just move back and forth between these 2 nodes. So we need to revise this approach a bit. We just need to add a new data structure, which is explored set. Once we consider a node by removing from the frontier, we add it to the explored set, so that we will not consider that the same node in future. So in this way, this is very similar. Let me exit this app. Okay. So here we see that when we remove a node from a frontier and we check that this is not the goal set, we add this node to the export set, so that we can make sure that the same node is not explored more than once. Now we closely look at this step while we remove a node from the frontier. In the previous examples, we just arbitrarily choose a node to remove, but now we see that this step is very crucial, and the performance of the search algorithm depends on this step. So one of the possible implementation of the frontier is a stack data structure, which is known as last in first out data type. In this data structure, the data which comes at the last will be removed earliest. So if we use stack as the frontier, we see that the performance of the algorithm will be in this way. Now we see that there is frontier and the export set. So we start with the initial state A, then we consider the state A, and we check that this is not the goal state. So we add its neighbor to the frontier. These steps are similar. Then we consider B. Now we add these 2 nodes in the frontier, and if as we told that we now use this frontier as a stack, and in this example the node D enters this stack at the latest, so we consider this node at the first. So we consider D, and then we add the neighbor of D, which is F, to the frontier. Now this node F is the node that comes at the last moment. So we are now considering this node F, and after considering node F, we see that this is not a goal set, and we also reach at a dead end. There is no unexplored neighbors of F. So we backtrack to our previous point, which in terms of this algorithm, we will keep our attention to the node C. We are considering node C, and we are adding its neighbor E to the frontier. And now we consider E, and we find that this is our goal set. So if we closely look at this algorithm, we see that if we use our frontier as a stack, then this is works in a way that we consider one direction deeper until we reach a dead end, and only when we reach a dead end, then we backtrack to our previous decision points. So for this reason, this algorithm is known as depth first search. because it tries one direction until it reaches a dead end. Now we'll see another variation of this algorithm, which is works in a different way, which is known as breadth-first search. So this algorithm expands the shallowest node in the frontier, as opposed to the depth-first algorithm, which always expands the deepest node in the frontier. To implement this algorithm, we will use another data structure known as queue, which means first in, first out. In simple terms, in this data structure, the node which comes at the earliest will be considered first. So now we'll simulate the same problem with our frontier as a queue, and these steps are very similar. Now at this point, we have C and D. Both of them are among them C comes first, so we consider C and add its neighbor E. Now we have D and E in the frontier, but the D comes earlier than E, so we will consider D first and add it neighbors F. We will see that F is not the goal state. Now between E and F, E comes first, so we'll consider E, and we see that this E is our goal state. So this we see that this algorithm takes one step at each direction before taking the second step at a particular direction. So now we will consider this maze problem, where there is we see that this is a grid, and these black cells are free cells which our agent can move, and these gray cells are blocked, which prevents the agent to move. And our search problem is we need to find our way from starting A to ending at cell B. So what will the depth-first search algorithm works in this problem? So the depth-first algorithm will from A it start to explore in this way. And to this point here, we see that we have two possible directions. One is to the left and one is to the right. Here we assume that arbitrarily the algorithm chooses to explore the left option, then it continues in this way. Now in the same way, it had to decide from left to right. We assume that arbitrarily it chooses the left option and it moves. Now it reaches the dead end, so it backs up to the latest decision point, and now from here it explores the right option. Here it also come to another dead end, so it backs up to its previous decision point, which is this point. From this it starts to move right, and here it has similarly it has two options to choose from, and it arbitrarily chooses up and gets dead end. So in this way, the depth-first algorithm will explore a particular direction until it finds a dead end. Here is another dead end. So there is a possible this is a possible working of the depth-first search algorithm. In the previous example, it was successful to find the goal set. Now we see another example where in the first step it needs to choose between two options, going up or moving to the right. If it is unlucky and arbitrarily choose to move up, then it continues to move in the up direction, and this is a possible way that this first search might find its way to the goal state B. But we see that a shorter path is available, but it was not, in this example, it was not discovered by depth first search. So we see that the depth first search might fail to give us the optimal result. So now we see the same example for breadth first search. We already know that the breadth first search explores one step at each direction, so it will move one by one in each direction, and in this way it will find the best solution. But here is this example which shows the limitation of breadth first search. In this example, as the search progresses, we see that it explores all the nodes before finding the goal state. So although breadth first search can give the optimal result, but it might take too long to explore many unnecessary states. So from this observation, we'll try to improve this breadth first search algorithm. We see that this is the snapshot of the search where the breadth first search need to choose between two possible directions, and in case of both breadth first search and depth first search, there is no way to judge which of these moves might be more closer to the goal state. So from this observation, we will start our discussion on informed search. The two search that we already see are known as uninformed search, because they do not use any problem specific information other than those that comes obvious while exploring the search space. But we will try to design better search method, which we call informed search. We will use the information hidden inside the structure of a problem. So this idea of using problem specific knowledge is also known as heuristics. So one very simple implementation is greedy breadth first search, which judges multiple states based on a heuristic function, which gives us an estimate of how close a state is from the goal state. So it is not possible to calculate exactly how a state is far from the goal state, but we need to use approximation to get an estimated distance of a state from the goal state. So we again see this maze example. Let us consider these two states, state C and state D. We human can judge that this state D is more closer to our goal state than state C. But how an AI agent can understand this? To understand this, the agent needs to have some extra information. For example, if we provide the geographical coordination of each cell to the agent, then it might use some approximation to estimate the distance of a particular state from the goal state. In this example, the approximation is known as Manhattan distance, where we are ignoring the existence of these block walls. We are relaxing the problem. We assume that there is no blocks. We are just counting how far the a particular cell is from the goal state by counting the vertical cells and the horizontal cells. This is known as Manhattan distance. This is just the summation of difference between the x coordinate and on y coordinate. So if we use this Manhattan distance as a heuristic or as an approximation to estimate the distance of a particular state from the goal state, then we will see these values. Here each cell is annotated by the Manhattan distance from this state to the goal state. We see that here the cell 2 shows that the goal state might be just 2 cells away from this cell, this state. This is not the correct information, because we see that there is a wall, but this gives us an estimate of the distance of a state to the goal state. So our greedy best first search algorithm will consider these values to choose which cell should be considered first. So it progresses in this way. At this point, it sees that it has 2 options. Here it costs 11 and the left cell costs 13. So as 11 is smaller, it chooses to explore these 11s, and the search progresses. And at this point, it chooses this 7 arbitrarily, because this 7 is also same, and it goes there and it finds the dead end. Then it explore the other 7, and we see that the search goes pretty well in this example. But here we see we find a dead end by following these approximated values. So in this way, eventually the algorithm were able to find the goal state. But there is also some pitfalls. Consider this example here. Based on this Manhattan distance values, the greedy vectors algorithm choose this path as its solution due to its lower value compared to this value at this path. But we see that the other path, although at this point it shows 13, which was greater than 11, but eventually this path was smaller than the path selected by greedy vector search. So from this observation, we are making an improvement of this algorithm, which we call the A-star algorithm. So we see that one of the drawbacks of greedy best first search was it only considered the heuristic value to judge which state should be explored next, but it ignores the cost that already incurred to reach at a particular state. So while designing A-star search, we make sure that it uses more information than the greedy best first search. So it uses 2 pieces of information. One is cost to reach a particular node, which was ignored by the previous search, and another one is the estimated cost, which is similar to the previous search value, previous search algorithm, where we need to use any heuristic function. So now we will see how the A-star search algorithm works. Here we see that in this yellow cell, we show the value of the cost incurred plus the value of the heuristic. So it chooses the next state based on the sum of these 2 values. So at this point, if we want to choose 11, then we need to consider 6 plus 11, and if we need to consider this state, we need to consider 6 plus 13. Among them, 6 plus 11 was smaller, so it starts to explore in this way. But we see that at this point, if the search has to make a decision between this cell number 5 and this cell number 13, we see that here at this stage we need to choose this between these 2 states, 6 and 13, and we see that this, although this heuristic value is smaller, but we need to add the cost incurred, which is 15. So 15 plus 6, and here the cost will be 6 plus 13. So 6 plus 13 is smaller than 15 plus 6. So at this point, the A star search will choose this path by leaving the previous path. At some point, it considers a path in both direction based on this value, but eventually we see that the heuristic value from this node starts to getting lower, and the A star algorithm fixes this path and it finds its way to the goal state. So we see that A star search algorithm can work in a better than the previous algorithm, but to get the optimal solution, we need to make sure that our heuristic function, which is Manhattan distance in our example, any approximation can be used here. The heuristic function need to satisfy these two conditions. One of them is the heuristic function needs to be admissible, which means it can never overestimate the true cost. It can underestimate the cost, as we see that in an example where the it estimates that just the goal state is 2 cells far, but there was a block between them. So it can underestimate, but it can never overestimate. And the second condition is it needs to be consistent. For example, for every node n and its successor node n dash, which is c cost apart from the node n, we need to make sure that this condition must be fulfilled. This condition is like very similar to triangular inequality condition. So if we can guarantee that these two conditions are satisfied by our heuristic function, we can be sure that we will get optimal result from this A-star algorithm. So there are other variations of informed search algorithm which might be works better in a specific situations, and there are also some improved version of A-star algorithm which improves the memory requirement, but we will not touch those algorithms due to time limitation. Now let us just see some Python codes of the concept that we already see. I will share these codes with you. Here the Python code is very similar to pseudocode. So what we usually express in pseudocode is it's very similar to Python code. So here is the class node which stores our value required for the search algorithm to work, and here is the our stack frontier. The main thing is this remove function, where we see that it removes from the end of the list, and the queue frontier which inherits the stack frontier. This is object-oriented programming. So by inheriting stack pointer, it achieves all its functionality. Just it need to make difference in the remove function, where we see that as opposed to stack frontier, this queue frontier just removes a node from the beginning of the list. And here is a class for working with maze example. You can play with this code. This code constructs a maze problem by reading a file. There are 3 maze problems are given in this example. In this text file, the A is the initial state, B is the goal state, and these hash cells are blocked, and these empty cells are the cells that you can move. The maze 2 is a bigger instance, and maze 3 is smaller instance, but it is a bit complicated to solve. to test this code, we see that this code takes a command line argument of the file name, which is the instance of the mesh problem, and it solve this problem using this solve function, which is the Python implementation of the pseudocode that we saw in the slide. The concept is very similar with the pseudocode, so I'm not discussing this code in detail. Just I will run this code and show you how the output might. So to run this code, we invoke this mesh file with a name of the input file. So it solves this problem. It shows the number of explored states, and it shows the solution here in a using string. It also stores the solution in a graphical format in this file. So in this example, this the black cells are the blocks, and the white cells are the yellow. White cells are the empty cells, and the yellow cells are the path chosen by this algorithm. So here you can choose to work with depth first search or breadth first search. In this code, there is a line where we choose the frontier. Yeah, in this line number 127, here at present it is using stack frontier, but if you choose to use here the cube frontier, then the algorithm will behave in best first search manner. So we'll return to our discussion on informed search algorithm. So far, we see the search problem where we have just one agent which is trying to find a solution for a particular problem. Now we'll see another types of search problem, which is known as adversarial search problem, where we have two types of agent. One agent is trying to achieve a thing, and the second agent is trying to achieve the reverse objective. For example, we can consider our favorite example of tic-tac-toe game, where there is two players. One player is cross player, and another player is O player. The cross player is trying to make 3 crosses in row, and the player 2, which is O player, is trying to either stopping the X player or places 3 O in a row. So this is let's consider a gameplay. Let's consider that X player at first picks the middle cell. At next step, O player picks this cell. Now we need to think, how can an AI program intelligently decide which cells to select next? So if the X player now select this cell, and the O player sees that it might achieve 3 X in a row, so in order to block X, it place O in this cell. Now if the X player plays intelligently, then it will place the next X on this cell, so that it can achieve its objective in two options. One option is this vertical, and another option is this horizontal line. So in this state, the O state cannot stop the X player, whether whatever it chooses to select its move. So we are now considering these types of search problems, which is known as adversarial search problem, and we will try to develop an algorithm which is known as minimax algorithm. To develop algorithm, we need to convert our problems into the language of computer. We know that computer can only understand numbers, so we represent the outcome, final outcome of the game using numbers. For example, let us say that the player which marks O, if the yeah let's assume that O player, if the O player wins, then we will denote it by -1. If none can win, we denote the final outcome as 0. And if the X player wins, we will denote the final outcome as 1. So in this way, the player X is trying to maximizing the value of the game, and the O player is trying to minimizing the value of the game. So based on this convention, in this example, we will call the X player as maximizing player and O player as the minimizing player. In the similar way as we discussed in the previous topics, we need to convert the description of the algorithm in a way that a computer can understand. So here we also have an initial state. We will have a function known as player, which takes a state as input and it returns which player needs to pick a move next. We will see examples very soon. Another function is action S, which returns the legal moves which is available in state S. And the transition model is again we represent transition model using result function, which takes a state A and then action A, and it returns the state after executing action A on the state S. And we need to know whether the game is over. For this, we have a terminal function which checks whether a state is the terminal state or we need more times to end the game. And we have utility function which gives us the numerical value for terminal state. So we need to consider that we have utility function applicable only for terminal states. So to get a value of whether a player gets +1 or -1, we need to consider all its ways to the until we find a terminal state. So in this tic-tac-toe, the initial state is this empty cell. The player function, if we give the player function this empty state, it will return us the X, because in this game the X player first takes its turn. And similarly, if we give this function a board where the O player need to make a move, then it will show us that O player need to do action in a particular state. And the action function, it takes a state. For example, this is a particular state of the game. The action function judges which player needs to play. We see that now the O player needs to make move, and it has two possible cells to pick one. So the action function gives us two possible moves. Now let us see the result function, which takes us a state and an action, and it gives us the resultant state. For example, if the O player choose to place O at this cell, then the resultant state is like this figure. And we have a terminal function to know whether the game is over. So in this example, this game is not yet over, so here the terminal function returns false. And in this game, we see that already the X player won, so this is a terminal state. It returns true value. And for utility function, in this example, we based on our convention, we set that maximizing player is X. So in this state, the X player wins, so the utility function here is 1. And in this example, the O player wins. So based on our convention set earlier, here the utility function is -1. Now we need to know how a player decides which action should it select to get its optimal output. So let us assume that now player O need to pick a move. So it tries to get the minimum possible value. So it has two possible options, but it does not know which option will give him the lowest possible value. So in the second level, the algorithm works in a recursive way. In order to know the mean value of this state, now we need to simulate the gameplay of the maximizing player, which is the X player. So if X player was to choose a move from this board, and we assume that both the min and max player plays optimally. So from this state, the X player had to choose this option. This is the only option, and here we get a terminal state. And for the other possible option, other possible state, one thing I need to mention earlier, but once we get a terminal state, we get a value, and this value is propagated upward. So from this state, the max player can achieve value 1. Now we consider the other possible game playing of maximizing player. From this, we see that none can win. So for this state, the utility value is 0. That means from this state, the max player can get 0 value. So now we again return. We are returning to the main player. The main player was simulating the actions of the max player in order to pick its optimal value. The main player shows that based on these two actions, the max value here is 1, and for the right action, max value is 0, and it will choose its optimal value. And in this example, the optimal value is 0. So in this way, the mean value, the mean player will choose this action, and it will get value 0, which means it cannot win, but it prevents X from winning. So from this state, the mean value is 0. But as this algorithm works recursively, this whole scenario might be a small fraction of a larger scenario where the max player is trying to decide which actions to choose. And in this example, the max player has 3 possible options. For 3 options, it simulates the game playing of the minimizing player, and it sees that the third option, which is the rightmost action gives its the optimal value. So it chooses this option and it gets the value 1. Now we represent these concepts in a more abstract way, because not all adversarial games will be in the similar fashion as tic-tac-toe. So in this abstract representation, we represent the maximizing player as a triangle pointing to the upward, and we represent the minimizing player as a triangle pointing downward. So in order to know for the maximizing player which actions is optimal, it considers these three states of the minimizing player, and from these three it sees that the here 9 is the maximum value, so it choose this action as its next operation. Here we see that a more large example, where the previous example was very smaller. It assumes that the game just need 1 moves to end. In this example, the game need 2 moves. First, the minimizing player takes a move, and then the maximizing player takes a move, and after that the game ends. So in this example, the minimizing player chooses its operation by simulating the gameplay of the maximizing player, and it sees that its 2 possible options yield 9 or 8. So between these 2 values, it chooses these 8 values. Now we can formalize this idea into an algorithm. So the minimax algorithm chooses its decision based on a particular state X. The max player picks action A in among the legal actions available at state S that produces the highest value of mean value, a mean value of the resultant state. And in the symmetric way, the mean player picks the action A among the available options that produces the smallest value of the max player of the resultant state. So here is our max value function, which gives a value based on a particular state. At first, it checks that whether the state is terminal state. If it is the terminal state, then it just returns the utility of the state. But if it is not the terminal state, then it needs to simulate the gameplay of the mean player and choose the maximum possible value among those simulation. For this, it takes a variable and initialize with -infinity. Now it considers each actions available for that state, and for each action it simulates the gameplay of the minimizing player and see whether its value gives it a larger value than the previous stored in a variable v. The function mean value is very similar, just it's the opposite version of the max value function. Here, for each state, it simulates the gameplay of the maximizing player from the resultant state, and from those states, it just picks the value which is the minimum. Now we will try to make some optimizations in the minimax algorithm, because it for a real world problem it needs to explore a huge number of nodes. So we are trying to save some of our operations by keep tracking of some values. To get the idea of the observation, let us consider this example. Here we are considering the gameplay of maximizing player. It has 3 possible moves. For the first move, it now needs to consider the game playing of the minimizing player, while the minimizing player considering its actions and see what value the maximizing player gets, and from these three values it picks the 4 because it is the minimum of these three value. Now the max player know that one of its action might lead its value 4. The next action, it also simulates the mean player in a similar way, and it gets 3 as the minimum of these three values. And for the last actions, it simulates the mean player and see that the mean player will get 2 value. So from this 3 value, 4 is the maximum, so it will choose this action, and the max value of this state is 4. Now if we closely look at this example again, we see that after exploring the first actions, it knows that the first action will give him 4 value. Now it starts to explore the second action. While exploring the second option, it sees that the mean player first gets a value 9, then the mean player gets value 3. This is the red signal for this max player, because it knows that this mean player will play optimally and it will select the lowest value. So if as this value is 3, we do not need to explore the unexplored node, because we already know that whatever the value of this state, the value of this mean value of this state will not be greater than 3. So we can safely prune this node and all the nodes below these nodes if those nodes are available in a deeper tree. Now it starts to explore the third action, and it in a similar way it gets 2, and once it gets 2, it is a red signal for this max player, because it knows that whatever the value of the other 2 unexplored states, the mean value will choose the minimum, and this value might cannot be greater than 2. So in this way, the max player can select some nodes which are unnecessary to explore, and it can prune those nodes. Thus it can save some operations. That's why it is known as alpha beta pruning, because it continuously keep track of 2 value, and it based on this 2 value, it prunes the nodes which is not necessary to explore. Regardless of this alpha beta pruning, we see that in case of real world adversarial scenario, we have huge number of states to explore. If we consider this simple tic-tac-toe games, we find that it has more than 255,000 possible games, and we know that the minimax algorithm need to simulate each of the game to reach the terminal state in order to know the optimal move. And for chess games, the all possible game is more than a huge number. This is just the lower bound of the all possible games for chess. So whether we using alpha beta pruning, we still cannot make a tractable intelligent program. So what we will do is we will be trying to develop an approximation of minimax version, which we call depth limited minimax. In this algorithm, we will not explore all the states until we find a terminal. Rather, we will fix a value of as a parameter. For example, if we choose that, we will just explore 10 state. Then after exploring 10 state, we will give the value of the state based on the situation of two players in that state. For example, in case of chess, if we decide that we will not explore more than 10 state, then after 10 state we will see that which moves are there in the board, how many positions are still alive in the chessboard, and in this way we will score that state based on our convention of min max. For example, if we choose that the black player is max and the white player is min, then if we see that a particular state where the black player is playing very well, then we will assign a value 0.8, which is close to 1 but not 1. So if we design a good approximation to judge a state, then we will get a reasonable algorithm to solve our adversarial search problem. This is the evaluation function which I told as approximation. It just analyzes the state which is not a terminal state, and based on its approximation, it gives us an utility value, and the performance of this depth limited min max algorithm heavily depends on this evaluation function. If we can able to devise a good evaluation function, then our agent will play in a reasonable way. And with this, I would like to conclude my lectures. I'm grateful to the Harvard CS50 AI materials. I use those materials in while preparing these lectures. Thank you very much. If you have questions, you can discuss your comments or your thoughts. Yes, I will share the slides and those source codes. I will highly encourage you to play with these codes. These codes are very similar to English language, so you can change those values and see the performance.
So if there is no question, then if you have any question, then please ask. So I believe they are so happy with the with this talk, as it is clear from their comments, and in fact I was also attending the same, and we would like to thank you, sir. And
thank you very much, ma'am.
Yeah, thank you so much, Professor Ali, and I'm sure we will keep continuing our collaboration, and we will be able to have many more such lectures. Thank you.
Yes,
thank you so much.
You are very welcome.
Thank you.
Thank you all.
Thank you.
Thank you so very much, Dr. Nayeem. In fact, I was on a call, so I could not this talk with with you. Thanks for your wonderful lecture. And to all the participants who are attending, sincerely, I wish to tell that we would like to share with you all. We will share with you all the links, video links, but not the PPTs, because we are in the process of e-content development in the same area. And therefore, we would like to utilize the expertise and the material that experts have prepared for creating our e-content, right? So that's the reason we are going to share with you only the video links, okay?
And also there is a question that, okay, if we can just revise and ask any doubt tomorrow. See, you can revise, surely you can revise, and please let us know your doubts. We will pass on your doubts to the respective experts, because these experts will not be available next day, right? So, but we will send your questions to them, and hopefully you'll get reply to those questions.
Yeah.
But again, the speakers will not be available next day.
Yeah. So on behalf of Asia Connect project team, we would like to thank Dr. Nayeem, and hope to get your support in future as well. Sincere thanks to you and Professor Yunus Ali, who suggested your name. I'm sure that participants have enjoyed your lecture. With that, I wish you all a very good evening. Enjoy your evening with your family and friends. Weekend approaching tomorrow. I hope you will have a good time. Thank you.
Thank you. Good night.